Good morning, everyone. Thank you very much for the introduction. I think before I'm going to start my talk, I thought on behalf of the UK participants, I would also like to thank the organisers very much for setting on up this wonderful meeting. As you'll see in the programme, it's got today and tomorrow have got slightly different themes. Today is the technical, more technical aspects. Hopefully, if you come from a clinical background, we will do our best to explain some of the advances as well. Really important for this meeting, it is interdisciplinary, which means we're trying to communicate between the two. So there's no such thing as a stupid question either. So put your hand up if you don't understand. It's all about that we go away understanding how the artificial intelligence, how it's closing the gap, this gap between the clinical need and what today's technology can also produce. We're really interested in closing that gap so that we can start to get more tools out into clinical practice. And just from my personal point of view, this is our third meeting. Our first meeting was the 5th and 6th of March 2020. And if we all go back, this seems more like a decade ago because this little thing called a pandemic has been between about that date. We weren't sure whether we would travel then. I made it. Aris, who's over there, he didn't make it. It was starting to open up. And we managed to get back before the UK was closed down. So that first meeting has, it seems much more than the true calendar date difference as to what's happened. But what also I think's happened is, despite all the disruption, research has been carrying on. There's wonderful advances. You're going to hear about our own project has been over that period as well. You'll hear about some of the work that some of our fellows have been working on. You'll hear more about that tomorrow. But I think it's quite important when we've all had our lives affected in different ways to also realise that people have been carrying on, and with the type of thing we were also working on before. So today and tomorrow, our workshop, it's partly talking about advances in the field. It's got some new people together, which is wonderful. It's about networking, it's about finding new connections. This is also about the capacity building in this interdisciplinary area. That's really important. It's also about debating. So everyone needs to speak up, participate, not just listen. You're welcome to listen as well, but we would also really like this to be highly interactive. So with that, I think I'm just going to step aside now because I think I'm the organizer of the overseeing my keynote, making sure I stay to time, is now going to be stepping forward. Thank you very much.
Thank you, Professor Alison, for your overview and objectives of the workshop. I would now like to invite Professor Shinjini Bhatnagar, Professor of Eminence at THSTI and the co-PI of the Calopus project and chief organizer or mentor, to give some welcome comments.
Thanks, Condi. I'm not a chief organizer. I've just been standing behind the curtain and screaming and shouting like you saw me just now. So just to set the tone of the workshop, thank you, Alison. I know it is meant to be informal, interactive. Just feel free to ask questions. The speakers can decide whether they want it in between, or we've kept a question answer session after the talk, but just talk and interact. And we hope that at the end of the workshop, we have a few more collaborations and many more new research ideas. So thank you for coming. A couple of lines, I think we're going to be introducing Himanshu, but one of our other collaborator, who's also IIT Madras, has also partnered with us for sponsoring this workshop, and India Alliance has also helped us to sponsor some of the programs that we're taking forward. So with that, I'd like one quick word. I know I'm a bit of a stickler for masks, but just that we are all still going through the pandemic, would request people to maintain protocols as much as we can, particularly because we are indoors. We'll try to keep the ventilation going, enjoy mask-free environment outside near the banks, seaside, but we have masks at the counter and the sanitizer. Sorry, that's a little bit of my madness. Okay, so back to Condi and Bela. Condi and Bela will take us through the program.
Thank you, ma'am, for your comments. I'd like to introduce Dr. Himanshu Sinha, Associate Professor in Department of Biotechnology, IIT Madras. Himanshu is a long-term collaborator with us in Garbini, and he's trained in human genetics, but now he works in computational biology and data science. And it has been very nice working with him, Himanshu. I would like to invite you to coordinate the session of Keynote, which will be delivered by Professor Alison.
Okay. Good morning, everybody. Thank you for the nice introduction. So I was actually wondering yesterday, and I was talking to our colleagues here. Alison is from Oxford. I graduated from Cambridge, and I was so sad that this year Oxford won. In the boat race I'm talking about. But Cambridge has a better streak, I think. I think we have a margin of about 10 more wins than Oxford. But that's that apart. But I think Cambridge and Oxford have a very good relationship. I used to visit Oxford several times, just for fun, not for collaborations. But now I think we can have a collaborative project here, working from India, which is sort of strange. So just to introduce Alison, I think she was already introduced today morning. But what I would like to say is that her work in the field of AI in determining fetal development and medicine is exemplary, and we would love to hear what she has done in that field. Because what I feel, and this is my personal experience, I was never involved before coming to IIT Madras. I was never involved in maternal and child health. Thanks to Shinjini and her team, they made me go through that MBBS book of obstetric and gynecology and sort of said, this is your course. Start a course before you start collaborating with us. So thanks, everybody, and welcome Professor Alison for her talk. Yeah. And just for what Alison has said, that she would like questions at the end. So if you can all just hear her first, and then we'll go for a question answer session.
Am I supposed to have it? Okay, so as we've said, this is reasonably informal. I've given this title of Progress in Ultrasound Image Analysis, which allows me to basically talk about anything. But what I'm going to be talking today, and I'm presenting it. There are lots and lots of people behind it. Very much a close collaboration with Aris and his team. And what you find when you work in ultrasound image analysis, it's a little bit different than working in other areas of radiology, because it's the interactivity of working with ultrasound means that you aren't just dealing with reading images and being able to interpret images. If you're really going to be solving or providing solutions that go into clinical practice, you've got to understand how images are acquired and how they're acquired in real time. So what I think is happening over time is ultrasound used to be considered maybe the noisy version of an MRI image or a CT image. And now we're moving away to really separate out and show that there's some real questions that need to be answered that are very specific to ultrasound. And it's an incredibly exciting era. And hopefully through what I'll be showing you over about the next 45 minutes, will convince you that that's true. That's my goal. I put up this slide. I gave a talk at our first meeting, and it was about introducing AI. And I had this slide, and I was introducing what was the state of art of thinking of the world outside my little world of doing image analysis. And what the sorts of things people were talking about was that healthcare was an important application of AI. And we're only talking a few years ago. These examples were taken from 2017 and 19. So healthcare had been identified as real good application of AI. And then if you went and talked in radiology and you were talking to the clinical community, there was a lot of fear. It was like, as you can see up there, the doctor will see you now is a robot. It was about taking away jobs. It's all concerned that there will no longer be work. And then you had people making wild claims, and I was very pleased I got this one back from before. It says, here's why one tech investor thinks some doctors will be obsolete in 5 years. This was taken in 2017. We can all do the maths. So hands up, who's not got a job now on the clinical side. Clearly, this was not correct. Even at the time, it was highly controversial to come out with those sorts of comments. And then there was a little bit of talk about AI will change radiology, but it won't replace radiologists. And then, of course, there were talk about on the commercial side, by 2023, 2 billion the market would be, and the first FDA approved AI system. So I presented this 2020. Let's see if we now think about what equivalent would be today. If we now look at 2027, the market is really, really expanding fast. So commercially, the expectations are still there. But what I think is interesting is now we've moved away from fear to looking at trust. And that's a really important message, is that a lot of the conversation in the clinical community and on the engineering is about how can we make sure that the tools produced, you trust them. What is the notion of having clinical trust? What is the notion of how patients trusting AI systems? And from a technical point of view, it means there's a focus on reliability, explainability of what these algorithms produce. And so everybody now, it's become interdisciplinary. We're all thinking about it slightly differently. But I think it's really exciting that we've reached, in a relatively small number of years, this is 4 or 5 years, we've reached this point. Academically, we've been challenging the notion of what's published. The 2 publications there, the first one said basically everyone's publishing AI algorithms, but they're not very good. They're making too many claims. So there's the introduction that we discussed at our last meeting as well, is how do you report findings in a much more rigorous way? And that's a very driving point today in the academic community, in the people working on the technology side, is how can we get better at reporting our findings? And then there's another area that we will touch on today through one of the talks, is data governance. The notion that healthcare data is special. You've got to keep it private, but you also want to share it. You want to share it for good. The sharing for good aspect in our field is about how you take data from different hospitals and you build models of that data. But you do that in a secure way. And in the UK in particular, through our National Health Service, they're creating what they call trusted research environments that allow you to do that. And I think you'll hear more about those sorts of words in future. So this is a bit like the bigger picture, but I think it was quite interesting to see how it really fast for research through to practice, that we're seeing these changes in the conversation around artificial intelligence in healthcare. So what I'm going to talk about for the rest of my talk, I'm going to talk about how ultrasound image analysis has changed. And also at the end, if I've got time, I will also talk about, return a little bit to the bigger picture of how it's impacting healthcare. So if we look at the drivers of change in medical ultrasound imaging, they've always been the clinical applications. Those change a little bit with time. A few years ago, it was, for example, the Zika virus meant there was an interest in looking at the brain. More recently with the pandemic, lung ultrasound has suddenly become to the forefront, and a lot of advances in how you can analyze lungs with ultrasound. So you've always had clinical applications, and every so often a new one pops up. It's driven by physics, understanding physics of image formation. How do you get transducers that will see deeper into the body? How do you reduce speckle if you don't? That's the type of noise pattern that you see on ultrasound images, but it's also used to recognize structures as well. And how do you get the right balance and enhance structures of interest? You've also had this massive change that you can see at the bottom of the slide, which is in the miniaturization of devices. This is driven much more about consumer electronics. The 1998 machine there, which looks a bit historic as if it belongs in a museum, was the first machine that I helped purchase for my own research. And it goes all the way through now to wireless devices. And that's transforming because ultrasound can be used in all these devices. That's also allowing innovations as well. But the slide that I use regularly, if people hear me speak, they will see I will often refer to this particular figure because I think it beautifully summarizes how ultrasound is changing. You've got, this is from a market report, and you can see the years on the bottom. And you can see that you've got a change in who's using ultrasound. And it goes from the traditional, the ones in blue, go through like MSK, maybe rural primary care, some of the maternal health would be there if it was in a hospital-based environment, to this change over the period now, where you go, ultrasounds move to office-based specialists, internal general medicine, urban primary care, and then later on going into home care, community midwife, and urban primary care in developing countries, and finally to the consumer. And so you've got this bell shape, and this particular report talked about this is likely to happen. It's likely to happen because of the handheld ultrasound probes, but it also will only happen if those devices become simpler to use. And that's where the artificial intelligence part comes in. And that's where I work, and when I'm working with Aris, we're working on how do we start to get some of those advances. And what it really boils down to is what the problem today is. Ultrasound is still a tool for an expert. And we need to change that to mean it's a tool that any clinical specialist could pick up a probe, use it for the task they want to use it in question. And what gets me up in the morning in my lab excited is about how can we develop the technologies that will enable that to happen. And there's two areas that we focus on. One is summarized with this sort of cartoon figure here. If you've got skill level of the person picking up the probe against how you would like them to perform, you have people who work who are highly skilled and been trained, but if you measured them in the field, or you could do that, I'll come on to that later, they would actually vary a lot in practice in what they do. And what you'd like them all to do is always perform very, very well every day, every scan. And that doesn't happen today. So that you might say is a hospital setting, maybe it's a high income setting where ultrasound is in hospitals. It's really trying to make sure that you standardize people, or you standardize human computer interaction is the way I prefer to use it. It's about workflow efficiencies, QA, quality assurance of what you do is really important. And it can also be thinking about how you address one of the problems of workforce, which is ergonomics, and the fact that that sonographers who scan every day, their careers can often be quite short because of they're having to move their wrist and their arm around so much. So that's one important user. And then the other is over in the other figure, which is thinking about people who are not very skilled, meaning they haven't had a lot of training. They're the people you want to pick up the probe and be able to scan, and you also want them to be able to scan at a high quality every time. And these are two examples. These movements, shifts will only happen if you make the technology simpler. So the reason ultrasound's hard is because it's complex. You've got an ultrasound machine and there's a lot going on. And it's really non-trivial if you want to automate this, if you try to get a robot to automate this, to get the human-like capabilities for freehand ultrasound, because you're looking at a screen to see where the probe is, you're moving the probe, and you've got this interaction, the hand motion, the complex hand-eye coordination is required. And it's that makes ultrasound hard. Humans are not particularly naturally good at it. They have to be trained to do it. And we haven't managed to change that with time. So what I'm interested in is how can we simplify the use of an ultrasound device? And as I'm an engineer, I break it down into simple steps. Today, well, the whole process would be you guide someone, you search for something, have a torch in your hand, you move your torch around, you home in on something, you tweak the torch to refine it, which is your adjust and refine. Then you capture an image and then you do the quantification. So that's what ultrasound's all about. The research field generally focuses on the blue box. You've captured the image, can we interpret it? It doesn't look at the whole process. And until we look at the whole process as engineers, we're not going to be able to support the clinician who wants to pick up the probe and use the image. So my research is very much looking at this question. Let me just move on from that. So you have these then, if we start from the basics of probe movements, you've got two scenarios. We have the highly skilled setting where they move around, they know what they're doing, and we call that freehand scanning. From that, you capture a standard plane, or the plane diagnostic plane of interest, and then you would do this image analysis. And what's happened with time is the standard plane capture is now good enough that is now in some ultrasound machines. And Alison and I have been working on in this area for a while, and it's on, for example, this is now in a GE machine to be able to do that. If you look at what I'd call the minimally trained setting, the difference there, which is summarized here, this protocol, this scanning pattern you're seeing here is our Calopas protocol, the one that we've been exploring as part of our project. You train someone to do simple blind sweeps. So you have a T-shaped, and then they move the probe in straight lines to the pattern shown here, and also the curve. And so you end up with really a structured scanning protocol. Doesn't take too long to train people. But then that means from an image analysis point of view, you have to do non-standard plane image and video analysis. So you've made it easier for the human, which maybe there's a law in here, it's become harder for the computer. But the two together, it's the same amount of work. So we've shifted the work for the AI algorithm. And I'm now going to be talking about a little bit of the work we've done in the minimally training setting, and then I'll come back to the highly skilled setting. So our wonderful collaboration, this is a picture from a previous meeting. There's a story here for another day of how we got there. It started out with Shinjini and I met Shinjini. I was also working with Aris, with sort of, as things happen, things come together and we create something new. And we started off collaborating in person. A lot of our collaboration has been via wonderful Zoom. And it's also been pulled together as well by being associated with Garbini as well. So we've really been able to benefit from the past as well as pull things to the future. And tomorrow you'll hear some of the fellows talk. So I'm not going to steal their thunder, as they say. But the sorts of thing we've been looking at is how we can look at some of these protocols, optimize them for video acquisition, trying to bear in mind from the AI aspect of how we want to be able to extract information. We've developed a way of detecting breach, which we will be we'll be able to report formally soon. And we've also looked at things like detecting low-lying placentas. And Alex, who's talking later, has been working on that. And this is just one slide of Alex's work, where what you're seeing here is the blue and the green. The green is the placenta, the blue is the bladder, and it's automated segmentation on a video sweep, and that the video sweep is shown at the top. And but beyond being able to see the red dot here is the lowest point of the placenta, and the idea is to be able to use the image analysis to identify that point to see if it's too low on the placenta. But in terms of this, what I mentioned earlier about algorithms not just producing a result, but also being able to explain the result, one thing that Alex looked at was he could map the feature representations that you learn from machine learning into a plot that's like this. It's called a TSCN embedding. And then he could group together some of his results to allow him to explain why in certain cases his algorithm failed, in other cases they worked. And particularly what's shown there as B, there was a cluster of features of types of placenta that his algorithm was not able to segment, and he could explain that it was to do with the shape of the placenta. Now, for humans, describing the shape of a placenta can be quite complex, but in the world of the computer, it would be describing it in terms of features. And because he could cluster them together, he had an easy explanation for why his algorithm failed or not, which would have been quite hard to do if you tried to write it down in the normal human terms. So that was just to throw in there an example of thinking about using machine learning explainability to advance your understanding of performance of an algorithm. Another project that Alison and I have been working on is called Tracer. It's a Tracer device is shown on the far side. It's a portable notebook with a wireless probe, very low cost probe, about $850, made by a company called Content. And the particular problem we were interested in looking at was coming up with a cheap, portable, ultrasound-based way to estimate the gestational age of a fetus. Importantly, estimating the gestational age across pregnancy. So women turn up, you don't know how many weeks pregnant they are, you want to be able to estimate gestational age. And for those who are on the engineering side, why gestational age is important is sort of summarized here. It's a fundamental thing you need to be able to know to determine how you treat a pregnant woman when she arrives at a clinic. So we set out to develop this little device, and what we measure is what's called the transcerebellar diameter, which is known from the clinical literature to reliably estimate gestational age over gestation. But we wanted to make the device simple, which means that the people who use our device, they locate the head, they place the probe on, then they move the probe around, and you record an 8-second video, and that's all they have to do. So as long as they move the probe around, what you know in the video, there will be a plane in which you can find the transcerebellar diameter, and from that, we can then do the estimation. So within the device, we have two features, and the techie part's over there, but don't worry about it. The first bit is quality assurance. So for every video that's captured, we get them to capture 3 videos. You do an automatic quality assessment of the video to see if there's a good enough plane to take a measurement. And we've automated that process. From an engineering point of view, it's challenging because low-cost probes of the sort we're using are not out there in the field gathering data every day. So we had to build a solution from very limited data that we'd acquired in a clinical research study. So we used a technique called few-shot learning that doesn't require lots and lots of data. And you can build a solution with a limited number of what we call supervision examples where you've labeled. And from that, we could then develop, the supervision is then where an expert has gone through the video, found the frames that were good enough to take a measurement, labeled them, and then we go through and learn to find similar images. And then when you've got a new video, you would run your algorithm and it would say whether within that video, it's good enough. If it's not, you say retake. And the beauty of ultrasound is the retake is cheap. So you can do it on the spot. So you do multiple retakes to check you've got the quality of data. Then we had another problem, is our ultrasound images are quite low quality, which means it's difficult to take a measurement. And my very clever students came up with a way of coupling a low quality image with, a low cost ultrasound image with a high end ultrasound image. And then you train together to then map the measurement using influence by information from the high quality to take a measurement on the low quality. Technically, it's called the dual adversarial calibration method, and it allowed us to estimate the transcerebellar diameter and the head circumference on the low cost images with very good accuracies as well. So we put those two elements then, which are really engineering challenges, or quite interesting things for us to work on, but were now being put into this device and are being used in a study with collaborators in Kenya. And our collaborator will be speaking tomorrow with Aris. So you might hear more about some of the work then. So back to what I was talking about, I've talked a little bit about the type of thing we work on in terms of working for people who don't often work with ultrasound. So the key there is simplify protocols, develop the image analysis or the video analysis to work with that. Then the rest of my technical part of the talk will now be moving across to work that's trying to get people who are experts, get them standardized, get them more comfortable in what they do, in terms of always being comfortable that the images they acquire are fit for purpose and diagnostic as well. So the way I often introduce this is the different generations of introduction of the artificial intelligence or machine learning, as we would speak about it from the technical point of view, is the traditional model would be this. You'd start with a need. That's the need in this case is fetal heart image analysis. The little circle is placing a dot on the heart. You're moving the probe around, and you want to keep the changing color is telling you which plane of the heart you're in, and the little arrow going backwards and forwards is the phase of the cardiac cycle. So you start with a problem like that. You would then acquire lots of data in the real world, and then the focus would very much be on the middle of the machine learning. And if we look at that paradigm, that's the standard paradigm today. Start with need, gather lots of data, focus on the algorithm. And in fetal ultrasound image analysis, a number of problems I would say are essentially solved. There will be improvements who follow that type of paradigm. They are automating fetal biometry. And the reason I say they're partly solved is you will see solutions now on commercial systems. And similarly, the automated standard plane detection would also fall into that category as well, where you're starting to see tools that really assist the sonographers while they scan. But from a technical point of view, it doesn't mean that all problems have gone away. We need to go off and look at some other area. There are all these problems that I've listed here, and I'm sure the list could be longer, that need to still be addressed. The solutions today need human annotation. So every time you build a solution like this, the heroics, and this is to Alison on that table for our Colopus project, human annotation and all the sonographers who've also helped us. This is a barrier to being able to roll out solutions faster. So technically people are responding with saying, well, there are methods where you self-supervise. We aren't going to be talking about this today in this meeting, but it's a very big area of interest to remove the need for human annotation. Domain shifts, there are lots of domain shifts, meaning that you gather data from different sources. There's heterogeneity in there, different devices, sites, studies, populations, and that leads to what are called domain adaptation methods. You're going to hear more about that later this morning. We work with the real world. Our sister field of computer vision generally works with balanced data and lots of data. If you take data from hospitals, it has natural real world data imbalance. And it's really the early days of how we can manage that. Machine learning prefers to have equal numbers of each class. Then you can solve problems. If you have many examples of one and it's a particular rare disease, you won't have many of another. That's a real challenge. There's also a need for more realistic models. In ultrasound, that means don't make decisions on an image, use the video. So that means spatial temporal features and analysis. And that's going towards what humans do. Humans do not make too many decisions on ultrasound by a static image. They will they will run it in cine mode and video mode, and the human perception will be using the video. And the other thing you're always wanting, and I will retire eventually, and it will still carry on as the holy grail, with richer, more human-like descriptions. This might be recorded. I don't mind it being recorded. I do not think that problem will be solved in a decade. I think we'll still be working at 20 years, maybe. But you know, there's going to be massive changes. And what I'm going to be touching on now is talking about multimodal analysis. And I'll explain that right now. Have I just gone backwards, I think? Oh, no. So this is the current paradigm you will see if you go, most people working on. The one that, the multimodal one, changes this. You've got three of the elements. You bring the human back in now, which I think is the real important thing. Where you can get so far by data-driven approaches. If you want to do more, if you want to be more efficient, by that means less data, you want to bring the human back. And as someone who worked in the field before deep learning, which is the main machine learning algorithm a decade ago, I had a career before that. Young people don't believe there was anything happening before that. There was lots happening before that, was very human driven. And now we're bringing the two back together, bring the human in the loop, bring our knowledge of the world in. And that's really exciting. And it'll add, I think it'll again mean that ultrasound image analysis will become richer overall. So the way that, if you're doing that, it means you go away from just taking the ultrasound video on the screen to bring the human in. And I had this slide before. It's all about now systems thinking. We have a system here now. We no longer have ultrasound data stream. We want the human. The human is doing things. We've got human interactions here. And if you want to understand that, again, it's a really old idea. You've got to measure it, right? You can't improve anything if you haven't measured it. So we started a unique project where we said, well, if we don't understand what people do, we can ask them what they do. You hear so much back. But either if you don't think that's telling you everything or you don't believe them, you can choose which, you should measure it. And then everybody might learn more about why ultrasound's hard. And also that then influences your design of your solutions. And we've had a project for about 5 years, Alison and my team, where we've been trying to just understand sonography. And the way we've done that is we instrument the system. So we capture the ultrasound video, we have a motion sensor on the probe, so we can look at how people move their hands. We have an eye tracker, which is really has been very interesting to see where people look when they read images, but also while they scan. And we have multiple people doing that, so you can look at the variability between people, so you can start to look at skill. And we've also, on quite a reasonable sized subset, we introduced the microphone, because I was like, well, I want to know what they're thinking. And I guess ethics approval probably wouldn't let me to be able to put invasive markers and go into the brain and do brain measurements. Thought that might be going a bit too far. So instead we asked them to speak aloud. So we have audio. So at least we're capturing some information about what they're seeing, what they're doing. It's great to have that information. It's very real world, so it's quite hard data to work with, but we've also been working with that. So what you can see in the little table there is the diagnostic scan gives us traditional ultrasound video. We've got an eye tracker, tells us about gaze. The IMU, which is the accelerometer on the probe, tells us some information about probe movements. And the audio that's recorded, which can go to text, also tells us about speech. So this now becomes our data source we have. You can see the probe moving there. The little green dot is the gaze. And it's so much richer because it's not telling you that every pixel is important. It's telling you that little green dot is telling you exactly which pixels were most important to that person making a decision, then how they move the probe. And you've then got a much richer data set. So we've got two aspects of what we've been studying through this. One of it is sonography data science. We have a large amount of data. It's all the data has been acquired in a real world clinic. So it's not clinical research. We just get people to get on with their job, but we record what they do. And they've been fantastic at allowing us to do this as well. And we've got hours of video, hours of gaze data, hours of probe movement, hours of audio. And so from that, you can start to ask, why is clinical sonography hard to master? And it's just never been done before because it's never been measured. And then we can start to model that to try and understand aspects of skill. And also that can also inform you as to which assistive technologies are the most useful to develop. That's why I wanted to do it. So if you annotate, then you can have deep learning methods to annotate, label which anatomy is present in each frame. You can automatically annotate the data. You can then just do simple things like how long do people spend looking at each anatomy? That's what that pie chart is. But you can do other things and ask, for example, can eye tracking data classify the types of anatomy planes? So forget the image, just use the gaze patterns. One of my students has been looking at that. Where do sonographers look on a standard plane? There are standards out there, but we were interested in the real world, do people really look at what they're told to look at, or do they look at different things? Not to see if they're doing it wrong, but to see if there's a difference. And maybe you learn from understanding where people look. And also the eye tracker allows you to measure pupil diameter changes. And I'll show you an example there. So you can actually measure cognitive workload, which is how hard the task is as well. So here's an example of comparing, looking at standard planes, which are the standard images you capture in the second trimester and the third trimester. It's orange is third trimester, blue is the second trimester, if you can't read that. You've got a typical ultrasound image, you've got the schematic of the structures they should check. And then what's recorded in the graphs, I'm not sure that you can read it, is the percentage of times over many, many examples that someone's actually looked at the structure. And because we've got the gaze patterns and we could segment the targets out, we could actually look at how often a gaze point hit a target. That's how it was done. We were interested in the standards are defined for second trimester. For the third trimester, they generally follow the second trimester rules. There aren't specific third trimester rules. So we were interested in how they adapt them. And what you find is the bit that's circled there is that the midline, which is visible in the third trimester, but some of the other structures such as ventricle are not, then they refer back to the midline as like a reference point more often to be able to go backwards and forwards to check if they can see other structures. So there is an adaptation of behavior that's naturally gone on. Cognitive workload is this pupil diameter change. And it's sometimes called, it's mental load or cognitive workload refers to the psychological effort to perform a specific task. So if you've got a hard task, your pupil diameter will change. And so you can use eye tracking to measure this. It's quite a noisy measurement, and you have to do signal processing filtering on that. But we were interested in, can pupillometry in the wild, so in the real world, measure task difficulty? And can we look at some of the obstetric tasks to see if we could measure how difficult tasks were rather than being told that one task was more difficult than the other? And we just used a simple measure to do this. It's called TEPR, and it was just a pilot study, 14 sonographers, but they'd undertaken 518 second trimester scans. We could match the pupil diameter measurements to the actual events in the video. And then we self-define tasks as being easy or not. I think this is probably the microphone stop. I'll carry on. It's compared easy tasks with difficult tasks. Fetal biometry was declared as an easy one, where some of the more difficult tasks are fine-tuning, assessment of the fetal brain, etc. And what we found is using this particular measure, you could distinguish between easy and difficult tasks as defined here. And also that sonologists, sonographers with less experience, we could compare those with more experience. We did see that there was also a difference, that the people learning were focusing more, and this was reflected in what we measured. Another example of the work we've been doing is to take all this data and annotate it. So we take the scans, we semi-automatically annotate it because we have some supervision for a small set of data, and then we use a boosting algorithm that then will run learn from that to run over all the other data. From that, you end up with describing what anatomies looked when. You can then build graphs that tell you what are the typical transitions between one anatomy and the next. Does a sonographer always scan in the same way? Do experienced sonographers scan with different patterns than people who have been trained and been told to follow certain protocols? And we've published this paper that sets up the tools and framework to do that, which will now allow us to be able to look at skill in more depth in the future. What I'm now going to talk about is the assistive technologies, move from sonography data science through to talk about how we now can combine some of the different types of modalities together to answer certain questions. So if, for example, you take the video and the gaze together, you can ask the question, can you get the computer to predict where a sonographer should look? So by that, we use the video and gaze of experts. We learn a model of where they would typically look. And then given a video, we predict where someone would look on average. So on average, where the expert would look. If you have the video and probe, put those two together, you can look at the problem, can a computer predict where a sonographer should move the probe? Again, we've got expert data of how experts move a probe, who've recorded the video. You can then, given a new video, you can predict where an expert would move the probe. And then the video and audio allows us to look at describing images. So present an image or a video, we come up with a textual description, which is potentially a useful thing to be able to do if you're trying to communicate what's in ultrasound to someone who's not used to looking at an ultrasound. So we've looked at all those three problems. So the information from video and gaze is shown here. And as I've just said, what we do is we capture the data from experts, and then we've looked at a variety, which I think is my next slide, a variety of different ways. This is a very sort of technical summary of all different ways of being able to do this gaze, or sometimes it's called salient prediction task, which is then if you give an image or a video, place the gaze point or the saliency image on that. And we've developed models for the first trimester and the second trimester for images and video. And a typical output is shown here. And what you're seeing in this screen is the heat maps you're seeing, the two blobs, are the prediction of where someone should look. And the green cross that's moving around is the ground truth. That was where someone was actually looking. So you wouldn't normally have that. The idea is you would be presenting the hotspots and encouraging people to look at the hotspots as being the points of interest as you move the probe. And just at a high level summary, what I'd say we can do with the types of technique that we've developed is we can predict where a sonographer may look quite well for the first and second trimester. And the current open question then is having overlays of this kind useful for video guidance? And that's a particular problem. We have a project that's just started that will hopefully be able to answer in the next 12 months or so. Looking now at probe and ultrasound going together, we're now moving away from thinking about we've captured an image to now think about this ultrasound guidance part. Particularly the part we focused on is that adjust and refine probe. So you've come to something quite interesting. You then need to move the probe around. A lot of it's rotation and slight translation, but a lot of rotation, refinements to be able to say you're at a standard plane. And we've taken two approaches here. The two approaches are, one is sometimes called a control parameter prediction style method. The other is called landmark retrieval. If you do control parameter prediction, it means that you would scan with the video and then tell the person how many degrees to rotate the probe to be able to get to the standard plane. This might be well suited to a robot, but if you were told to move a probe 15.3 degrees, you probably can't do it too well. So the particular research fellow working on this was, he came up with a solution, but he wasn't happy with it because he said, well, no human is ever going to be using this. Instead, he proposed the other type of solution, which is a landmark retrieval based one, where here you capture an image and then the computer will tell you where you are on a model. So and the way you do that is you learn the relationship. You've acquired lots and lots of data around a model, and you've learned the relationship between the image and the position in 3D space on a model. Learn that that mapping is known. And then given an image you've captured, then you can place, or you can put a landmark on the model. Here's just a summary of some of the results, where it's easier to present how well it works in terms of, does the query image, the image you presented, equal one that's been retrieved, and how accurate is that, because then the mapping is straightforward. And here the images, the important thing here is the images look pretty close and close to the position. If you translate it into real measurements, you also find that it works quite accurately. This last example I'm going to show you of video, probe, and gaze is now putting the three modalities together. And this is really mimicking what the sonographer does. They interact between looking on the screen, moving the probe, looking on the screen, moving the probe. And that dual human action is getting closer to getting, if you can get the computer to work with that data and suggest what to do, then you'll be getting closer to mimicking how sonographers scan. So it's quite an exciting thing to be able to get to this point. From an image analysis point of view, what we want to do is to be able to link the information. If you were at time t = -1, you had an image and you had the gaze point at that point, you know there is a relationship between those two that connects with how the probe is moved. So there's a little triangle there where you want to be able to connecting the information. Then, having moved the probe, the next thing you would do is you'd have a new gaze point and a new image would be generated. And you can think about that, all the data, you want to find the interlinks and interchange between the three. And my postdoc, Quinn Hughes, what she's developed is a very elegant way of doing this, with the architecture shown here. But that don't worry too much. It has that triangle connecting the information. You learn the relation between that, and it predicts the two things I've talked about before, which is gaze trajectory prediction and probe motion as outputs. So you have what we call a multitask solution. And what she showed is, compared with the single mode, the video gaze or the video and probe models I showed you before, she compared with those directly. And the red line shown on the top figure is her algorithm in terms of accuracy. Its prediction accuracy is better than using probe and video together. And what's shown on the lower one is it's showing you the prediction error for gaze. Hers is the dark red at the end. The error is reduced if, again, you use this 3 bits of information. So we're starting to get to the point where we really are being able to model what sonographers do, and provide information back to them about where to look and how to move the probe. Final examples I wanted to give were on how we've used audio and video. And here, the information we have then is an image or a video and the audio that's been spoken over. You can use the audio as raw signals, or you can break that down into the words that are spoken. And what's shown here is the word clouds of words that are spoken in what we would call a closed world of sonography. Someone in a room, what do they talk about? So it's not a general description, it's specific to sonography. And so we take that representation then, text and images, and then you can again look at architectures that, given an image, will generate sentences. And Mohammed Al-Sharad, his thesis was on how can you do that. He's developed ways to generate sentences where the input is an image. He's also gone on and looked at video plus gaze. Gaze is a really rich constraint because the gaze is probably the thing you're talking about. So that means that you can really get richer descriptions by cancelling out some of the other words you might consider. By if you know that the gaze point is looking at a heart, then that will be suggesting the word heart should go into the sentences. So we've looked at the video. If you look at video, you have this different vocabulary as well. And we've developed, or rather Mohammed's led developing these gaze-assisted models that generate richer and more diverse captions. We're not trying to repeat what a given sonographer said. We're trying to generate sentences that you could plausibly say about that image or the video. So it's an acceptable sentence. It's not perfect, but I'm showing you academic research here, is to get across where we are. So if you could just play this first video, please. This is a ground truth, lots was said. This is the video, this is a spine. And then we come on to the different types of, the dumb algorithm declares the object a spine. That's the GL is gazeless. Then you get the ones that start to use the gaze, they start to tell you more about what's going on. And in each case, they're all plausible. Still quite simple. You wouldn't be taking this to a clinic, but it's starting to show the type of descriptions. Thank you. Can I move on to the next slide, please? The final one is audio video, which is very different. It's not really aimed at assisting clinicians. It's playing with data. I'll say it because it is playing with data. But it's also, if you're interested in this area, it's trying to understand what is the richness of the representation that you can build from this type of data. And the question we're looking at here is, can a computer localize anatomy from a learned audio-visual representation? And I've put in brackets, that's the show from tell. Now that all those words might have not been totally clear. What I'm saying is you've input is audio and video, and you highlight what someone was looking at without knowing anything about what they were looking at other than you had the audio and visual information. So simply, you take the audio and video, you predict gaze with no knowledge. None of the learning has known about the gaze. This is inspired by computer vision, audio visual representation learning, which is a very big area in computer vision at the moment. There's a sparse correlation between the sound, because someone's talking about what they see on the screen. It's not generated by the object, which is what typically happens in computer vision, where you might have a violin and you hear the music, and then it would highlight the violin in the object. The fetus isn't talking to us, so we're not got the audio from the object we want to explain. And you're really trying to see how well you can build an audio-visual representation, but then you put tasks on the end. And so in this case, it's speech-guided visual localization. So two of my team have been working on this problem, and I thought I would just show you how well that works. If I go to the next slide. And what you're seeing, the ground truth, which is where someone was really looking, is on the far side. Is there audio on this? If there is, can you start it again? Because we need it. Is it not going to work? Okay, there is audio. All right, we'll have to skip over that. Yeah, I guess I can't explain it. Maybe I'll, if anyone's interested, that they can come up to me later. But basically, you play the audio and the video, and what you're seeing there is where someone was really looking. This is generating on this side. The heat map is where the computer says someone was looking without knowing where they were looking. So that's the idea about that. So I think at that point, due to time, I will stop. I was going to talk about finishing another way, but that's just a summary of some of the things we talk about. Some of it's really trying to get devices out into the field, supporting need. Others going back to the foundation of really thinking about some of the basics of how you can build ultrasound image analysis as a solution. So thank you very much for listening.
Oh, yeah.
That was a great talk. I'll split my question into two parts. The first part is in typical healthcare way of doing things, how many of these are integrated into the real clinical workflows? So even though the last ones you are talking about it, that's one. And the second question I have is that a lot of these, at least the way ultrasound has been positioned, is that you want to push it to the point of care. So now when we talk about deep learning, at least it requires a little bit more computing than what is available in the point of care. So any thoughts on this?
So I think it's about how you get some of the methods out. I think the first part of my talk was addressing that and working with Aris. So we've developed, particularly the tracer device is a device being used in trials. That is on a consumer grade notebook. So to be able to do that, you have to make the model small, and then they will run. If it's a small model, you can. There are ways to be able to get models working that do not require a lot of GPUs, and there is a trend towards that for certain type of solutions. So I think that there are examples. Also, Aris and I work with a company, Intelligent Ultrasound, that we co-founded. That's their space as well. And they've also got some examples where they have to work hard on getting the model small enough. But also the big companies now are changing their architectures to try and make them, as they introduce new machines as well, to make them suitable to be able to add these sorts of capabilities and functionality into the machines. So you're perfectly right. That is a sort of barrier, but I would say that that's changing. There's also, but you can only, the models can be very big. In research, they might be. You've got to be able to get them to be able to reduce down. So that was one of your questions. What was the other one?
The other one was that so currently the main barrier for the AI is that by the time you launch the application, you get the inference. That time is longer than what a typical, let's say, sonographer will look at it and then say X is present or not. Right?
What do you mean the solutions are not real time?
Not real time and not integrated with the current workflows.
I think that's changing. I think there's a lot of effort going into being able to look at that. The examples I've given you are examples where they have addressed that. It's finding the right, solving the right problems. For the example I often give is there's a lot of efforts gone into automating biometry, and yet do people really need biometry automated, or would they rather have the help in how to scan? And if you ask them, the hard bit is getting to the plane. It's not taking a measurement on the plane. So, and that I think the academic research field is responding to, but it does require you to be able to have more access to an ultrasound machine and be able to not just take data out, but actually put things inside. Some of the companies are now also offering SDKs, so which is the software interface between streaming ultrasound video. So you can put your application together with that. That again is what we've done with the tracer, where it's our laptop. But the transducer data is linked in. So things are slowly changing. I think that is an area that in the next few years we will see go away as a problem.
Okay. It was really fascinating to see how you have analyzed the ultrasonologist gazing and working with the hand flow. So my question is that during your experience, did you find that while arriving to a particular plane, let's say you are trying to get a biothalamic plane or getting the transcerebellar diameter or cisterna magna, during that some important informations are lost when you are trying to focus on certain particular areas? Like I've seen during a lot of post-processing softwares which have been developed, then to get a particular desired structure in focus, a lot of other
Well, the most, if you look at most of the examples I'm looking at, I don't deal with, if you like, the diagnostics. We're dealing with guiding people to capture better planes. So I avoid that problem by working on different problems is a simple way to put it. So I guess the problems I'm most interested in is that human computer interaction where that would not be an issue. It is an issue, I agree. But it isn't a particular problem I've met in my own research.
So I work in gestational diabetes in pregnancy. So my very simple questions relate to that. You showed one slide on biometry, automatic calculation of head circumference and transcerebellar diameter. So do we have something for abdominal circumference and estimated fetal weight? Because this we take into account while treating patients.
We haven't actually worked on that problem. What we focused on looking at gestational age estimation from the brain. Some of our other work has also looked at the brain structures. So we haven't worked on that. That would go, I guess, more to do with traditional biometry. Is that correct? No? Yeah. Yes. Oh, and measure it. Yes, I don't see why not. So in fact, a lot of the, I think, you know, some of the more interesting problems is actually thinking about problems that are not doing the workflow of people as they do it today, but would be the new sort of point of care. I just want to do X. Yeah, I don't see why not. But I guess to make it happen, there has to be a big enough need to make it worth putting all that. Today, there's all that. I had a slide that said how much effort goes into developing and validating the cost of one solution. One of the barriers today is it takes so much to go through to, in your case, you'd want it FDA approved or approved from a regulatory point of view to use in practice. The cost of doing that for every single little task is too expensive. No company would take that on. So we've got to reduce the cost down that you could have a suite of capabilities that would allow you to be able to do that. And if you go from that to being sort of AI in making artificial intelligence like a human, you'd say humans can do that. Why can't we get an artificial intelligence system that's human-like enough that could just adapt its behavior? We can't do the adaptive behavior part, which is probably what we would need to be able to do your solution, unless you could convince someone that there's money in it, right? This is always the dilemma.
So, yeah, if may I add, Dr. Yashdeep, I'm Dr. Abhinav, I'm a radiologist. So yeah, we do have these kind of AI algorithms in progress. And I got to see one of them where you can actually measure the abdominal circumference apart from biparatal diameter and head circumference. The only thing is right now we need to focus on the correct plane. So it won't be like you just put the probe on the abdomen of the mother and you'll get all the data which you require. So you just need to focus on the correct plane, and then it does automatically measure and give you all the details, even including the percentile where it falls, the weight, the fetal weight and all.
I think there are many more interesting questions as well. But there is one which I want to take from the chat. So this is from Jyoti. She's asking, do you think it would be useful if algorithm can detect or screen for abnormalities in regions of interest or those areas identified to be clinicians' region of interest? This might be more useful in settings with lesser expertise.
Yes, that's a very good question, and it's always there. I think why it is, you could solve the problem. But you've got to place it in context of, if you did that, and whoever the person is with the probe, what would they do with that decision? Because it's no good having, you're in a pipeline of clinical pathway. So you can, again, develop a solution, but you'd also have to have the list of things that you would detect, and coming up with that list where you've got all the data. If it's rare, getting enough data to build a solution today, it's not easy to build these. Bespoke solutions are fine, general solutions are not. But I think if there are cases, those are exactly the sorts of problems we should be working on. So if people are interested in that space, they should go out and start solving some of the problems. So, the more people who work on the problems, the more likely we're going to have that suite of solutions we need in the future.
I think, yeah. So with that, I had a question, but maybe I'll talk to you over coffee rather than here. So I'd like to thank Professor Alison for her wonderful talk, and give her a round of applause. And then I think Condi will take over